In this video, we will be going over wind loads and just their general requirements for those wind loads. Again, this is found in ASCE 716, Chapter 26. Now, the reason we're only going to go over general requirements in this wind load video is because following Chapter 26, there are multiple different procedures for calculating the wind loads that you're going to apply to your structure. And really, the procedure that you used is based on the company that you work for, the type of structure that you have. And a lot of times, the company that you work for picks one procedure and they just stick to that procedure because that's what the engineers there know. So I don't want to go over one procedure and then have you end up using something else in industry, because they're going to train you in industry anyway. So we're just going to go over the general requirements that are going to be the same for every procedure. So the first thing that you're going to want to find as pertaining to wind loads, you're going to want to find your basic wind speed, which is denoted by a capital V. And this is based on your geographical location. And they're given in miles per hour. So this should conceptually make sense to you. If you live inland in the US versus living on the coast where you're going to see hurricanes, the wind speed is going to be very, very different. So there are graphs with these wind speeds given to you in figures 26.5-1A, -1B, -1C, and -1D. These are for mainland US and Alaska. -2A, -2B, -2C, and -2D is for Hawaii. And there's different maps for your different risk category of your building. So if you have a risk category 1 building, you're going to use map A, 2 is B, 3 is C, and risk category 4, you're going to use graph D. So once you pull off your basic wind speed from that map on one of those graphs, you can go ahead and find your velocity pressure at different heights along the height of your building. And this is given to you by using equation 26.10-1. And that equation says that your velocity pressure at some height above the ground Z is equal to 0.00256 kz times kzt times kd times ke times your basic wind speed squared. So let's just go ahead and go over these coefficients here. So kz is your exposure coefficient. And you can find that in table 26.10-1. And again, this uses z as being your height above the ground at the location that you're looking for on the building that you want to find that velocity pressure. A lot of times you want to find your velocity pressure at the eave, which is where it transitions from the roof to a wall. And so it's going to be that height there. Generally, not always. And then we have kzt, which is your topographic factor. Which you can get from equation 26.8-1. And these are all parameters of what the topography is like around your structure. So it usually has to do with structures that are sitting on hills or near hills because the wind behaves differently around terrain like that. And then next we have KD, which is your wind directionality factor. And you can pull that off of table 26.6-1. And that's based on your structure type. Then finally, we have our KE value, which is the ground elevation factor. And that comes from table 26.9-1. And just what that sounds like, it's based off of the elevation above sea level. Where your structure is being built. So if you're building on the coast, then obviously your elevation is going to be 0, but if you're building in the mountains, then it's going to be a lot higher, and then you can just pull your KE value off of that table. One thing to quickly note about that table is that if you look at the footnotes, it also gives you an equation that you can use, so you don't just have to pull it off the table. You can go ahead and just plug everything into that equation. And also, if you look at footnote number 3, you can conservatively take KE to equal 1.0 in all cases, and you don't have to calculate it. And so then once you find all those factors, you can just plug it in to that equation. Again, this V here is your wind speed that we found above. And you input that in miles per hour. Again, the units aren't really going to work out, but as long as you put this in as miles per hour, then your QZ will come out in PSF, which is what we want. Another thing that you'll need to know about your structure when doing wind design is its enclosure classification. And also, once you have your enclosure classification, you'll be able to find your internal pressure coefficient. Which the term we use for that is GC sub PI, which is also going to be important when you're doing your wind load design. But to find your enclosure classification, they do provide a table for you. Table 26.13-1. But what I personally like to use are the definitions given in section 26.2, because I feel like they give some equations in the definitions that make it a little bit easier to understand. But I'll go ahead and write all those out here so you have it in one place. So the order I like to check things in, I like to check to see if it's open, then check to see if it's enclosed, then check to see if it's partially enclosed, and then partially open. So these are the 4 different enclosure classifications that your building can be. And for it to be open, you've got to satisfy this equation, where A naught is going to be the areas of your openings on that wall, and AG is just the area of the wall, the gross area of the wall. For it to be classified as enclosed, it's got to satisfy this equation. A naught has to be less than the minimum of 0.01 AG or 4 feet squared. So you'll first compare these two, pick the smaller one, and then if whatever is smaller of these two is greater than A naught, then it can be classified as enclosed. And then I move on to, if neither of those are satisfied, then I move on to partially enclosed, which you have to satisfy 3 different equations. So A naught has to be greater than 1.1 times AOI. AOI is the sum of the openings in the building, not including the wall that you're looking at. And then it also has to satisfy A naught has to be greater than the minimum of those two that we talked about in the enclosed, which if this wasn't satisfied, then this is going to be satisfied, which is why I like to do the enclosed first before I check the partially enclosed, because then you've already done one of the equations. And then AOI divided by AGI has to be less than or equal to 0.2, where AGI is the sum of the gross surface areas of the building, not including AG of the wall that you're looking at. Again, these are found in section 26.2 under partially enclosed, that definition for partially enclosed. You can find the full definitions for that. And then if you checked open, you checked enclosed, you checked partially enclosed, and you can't get any of these to be satisfied, then you know you have a partially open building. So when it's not open, enclosed, or partially enclosed. And that's how you find your enclosure classification of your structure. And as I said earlier, once you have your enclosure classification, then you can find your internal pressure coefficient. And that you will pull from this table 26.13-1. And so for open buildings, your GCPI is going to equal 0. For enclosed buildings, your GCPI equals plus or minus 0.18. For partially enclosed buildings, your GCPI equals plus or minus 0.55, and for partially open, your GCPI equals plus or minus 0.18. And again, this will all be used when you do your wind load procedure. Again, we're not going to go over specifics of that just because there are different methods and I can't be sure which method you're going to use in the future. If you do have specific questions about a method though, you can head over to our homework help page and we'll be able to get questions for you answered there. Also visit our tutoring page and I'll be able to sit down with you and walk through one of these problems with you.